of our webinars. My name is Barry. I'll repeat that again just in case. Welcome everybody for the new episode of our webinars. My name is Barry and I'm an MCA Market Development with Shure, which is Musicians and Consumer Audio. Today's webinar is going to be very interesting. It's going to go, as we said before, under the cover. So a lot of the mystery of how microphone works is going to be uncovered today. So without further ado, I'd like to continue what we started. Just for your information, you can type in your questions anytime, but I will have to review them at the end of the session. So feel free to type questions anytime you want in the Q&A box. And once the presentation is done, I'll have a look into it and I will try to answer all the questions as much as possible. Now, moving forward, today I'm going to talk about starting with the polar pattern, but I know that we did talk about them previously and how they work with the microphones, but what I'm going to do is I'm going to show you how the cartridge is built to be responsive to a certain polar pattern. So I'm sharing my screen, so let's go here. Now, the first part of the slide here is going to show the standard diaphragm or the standard diaphragm in a omnidirectional microphone. And just to give you an idea what an omnidirectional microphone, again, is a microphone that picks up the sound from all the directions. So you do not need to aim the microphone to the speaker, just put it anywhere and it works. It's very much similar to how your phone microphone is. So everybody got the phone and the microphone, which is usually at the bottom, it is an omnidirectional. So that's why you can hold your phone on your ears and it actually still be able to pick up your sound. A lot of the people do this to the microphone and speak directly into it. Honestly, it doesn't make a difference. It only distorts the sound. All they need to do is hold your phone anywhere, this way, that way. It doesn't make a difference because the microphone doesn't have a direction. It's an omnidirectional. Now, why is it omnidirectional? Because the diaphragm is going to sense the pressure in the air regardless. So if you look at the picture in the slide here, you can see the speaker is kind of behind the microphone, but it's able to create pressure in the air, as in sound pressure, SPL, which can affect the movement of the diaphragm. It's the same way, let's say, if you're sitting in a room and you decide to go to the kitchen, which is part of the room or just by the room, and your TV is on. Are you still able to hear the TV? Yes. Is it as loud as it is? No, that's a completely different story. So loudness has nothing to do with directivity. It's something called the square inverse law, which is related to the distance. But in terms of, can you hear the sound? Yes. We sit in the room sometimes with the window open. You can hear the cars passing by. You can hear the salesman sometimes selling some stuff if you're in the market, or you can hear the birds. So the directivity of the sound is something that we can recreate by bending the laws of physics. Now, how can we bend the laws of physics in microphones and make the microphone be more sensitive to sounds than the others? So the idea here is based on something we call cancellation, or it's by playing with the phase. I've noticed we got a question on the web that was talking about explaining how noise cancellation works, which I did last time, but I'll be more than happy to do it again. So I'll plug in another mic here. Let's do the famous SM58 UAE flag. Okay. Check 1 2, check 1 2. You can hear my microphone really well. Now, this microphone is on mute. That means the sound is coming only from this microphone. But this microphone is out of phase, as in it's delayed with a certain time, or the signal is reversed. That's what we say when it's out of phase. So now this mic is here, it's working, but look what happens when I get closer to that mic. So now I'm talking with this mic, and you can see at a certain point when I'm close and the two mics are together here, that some of the bass response is gone. And there's a certain point, if I get the mic closer or farther, there's a point where the sound is pretty thin. But what happens when I take this microphone completely away? Check 1 2, check hey 1 2 1 2, check hey 1 2 1 2, check 1 2, hey 1 2. So there's a point where this microphone is messing up with the signal, and it's creating some sort of phasing. But because these two microphones are not really identical, you cannot have 100% phase cancellation. But if you have 100% two microphones and they're identical with the same gain structure, as in the same sensitivity on the input of your preamps, then you'll be able to achieve more cancellation than this situation. But here we were able to have something called phasing issue. Sound has started to change its tonality. Now, this kind of phenomena in physics is quite useful to create polar patterns. So that means what I need to do is I need the diaphragm on the microphone to not respond for when sounds are coming in a different direction versus when it's coming from the front. Now, how can that happen? Now, you remember when I said earlier is having a phase difference, either in time or you force it to happen with the hardware. So most of the mixers, they have a phase cancellation button on it. So you can just press a button and it will flip the phase. So what does that mean? That means if the microphone goes this way, the signal will go this way. And if the microphone diaphragm goes that way, the signal will follow it. But if you flip the phase, what will happen? It will go the other way. When the microphone diaphragm is going in, the signal will go that way. And when it's going out, the signal will go the other way around. So that's when you flip the phase or change the directivity of the signal versus the physical movement of the microphone, which is quite helpful if you want to eliminate usually feedback in a certain situation. If I have to stand close to a speaker and I want to eliminate the movement of the diaphragm of the microphone versus the movement of the speaker, it's a good idea to flip the phase of the microphone on your mixer. But you know what? Also, creating a delay from the speaker or by having distance, because the sound travels in time, and by the time the sound reaches to you, it might reach you in a different phase because of the delays. So now having a delay in the sound also creates phase. So that means I need to create a way to slow down sounds when it's coming from the backside of the microphone. While if the sound is coming from the front, it has to come without any delays. How does that help? It simply creates a phasing effect because the sound has to reach the front anyway, as I mentioned earlier, if I want to treat it as an omnidirectional microphone. So what I do in that case, I need to have a certain window for the sound to come into the microphone earlier or to come into the microphone later at a different time and a different phase or a different shape because of the delay. So look into the slide, you can see now if I hypothetically put a delay circuit at the back or delay effect at the backside of the diaphragm, in which that would cancel the sound of the front only if it comes from a certain direction. This would actually create a cancellation. So that means now my microphone can be more directional. So what I want to do, I want to subtract the front force from the rear force only when the sound is coming from the back. Now, let's look at how the SM58 or even the SM57 is built. I don't have a 57 here, but I'll open that microphone, which it becomes a 57. And I'll try to show you something here. If you look closely here, you can see that chrome window at the bottom here, that side, which is like a grill just to protect the internal part of the microphone from dust. But that is an opening to the microphone. And I'll do a demo in a bit. So I'll try to close it and let you hear the sound. So this opening, let's say we call it D, okay? This allows the sound to come from the backside of the microphone. But where is the trick? The trick is that we put a resistance, a material that has some sort of resistance to sound, which is R1. Now, R1 here is helping to delay the sound. It's an obstacle, okay? So when sound comes from the back, it will try to overcome these obstacles, and that will cause some sort of a delay. Now, we will do a simulation here, and that simulation is a sound coming from the back. On the left side is the omnidirectional, and on the right side is the unidirectional or a cardioid. Now, what happens here is the sound coming from the front meets the sound coming from the back at the same time, considering the delay, but in a different direction or in a different pressure direction. So one is pushing this way and the other one is pushing that way. What happens? They stuck in the same place. But if I'm pushing from one side, I'll be able to move. So it's the same thing. If I have anything, if I have that microphone here, if I tip it from one side, it will tip. But if I try to tip it from two sides at the same time, it will still stand in its place. And that what happens in a cardioid microphone with the delays created from the opening on the side here. So what happens when I'm directing my microphone to the sound from the back side, the sound coming from the back meets the one on the front at the same time, but in a different direction, in which it causes it to stop, stand still, or reject that sound, or be less effective. So I'll do a demo right now. So SM58 again. Actually, without the cap, it becomes like a 57, by the way. So what I'm going to do right now is I'm going to cover the window on the side here with my hand like that. Check 1, 2, check 1, 2. You can see that the tonality changed like completely. And now it becomes even more omnidirectional. I mean, I cannot completely cover it without tape. Maybe if I have some tape, it will be even more efficient. But you can see right now it's less directional. Check 1, 2, check 1, 2, check 1, 2, hey, 1, 2, 1, 2, check. While you can see that the tonality is completely different right now. Check 1, 2, check 1, 2, check 1, 2. You can see that now when I start twisting it to the side, you feel more drop versus when I'm holding it completely like this. Check 1, 2, check 1, 2, check 1, 2, versus check 1, 2, check 1, 2, check 1, 2. So you can see how much the effect of the delay in the back is helping the microphone to be more directional or to be a cardioid polar pattern. So you can see it's a pretty much simple idea that can be quite effective in that manner. And it's almost the same way when you walk into an apartment. When it's still empty, there's nothing inside that sounds so boomy and echoey until you put your furniture in and it becomes tight and quieter. And that means also it helps reducing noises traveling from a room to another. It's simply because you're creating more obstacles that would help cancel or help in diffusing the sound and canceling each other before it leaves the room. But when you have empty rooms, the material that is not there, which is your furniture, just helps the sound just travel the way it likes to, and then bounces from a room to another, and then you are able to hear more. So this is like a quick summary here Um, the consistency of polar patterns is not something easy, by the way. And a lot of people kind of take it for granted, even when they try to buy budget microphones, or even if I want to say the counterfeit microphones. When I say counterfeit microphones, these are the microphones that are built by other companies just to copy an existing product, which a lot of us are facing in the market, especially in some of the, let's say, very commercial markets or something like this. Now, what what is the difficulty here? The difficulty is that the measurements required to make a polar pattern very consistent is not easy. It requires measurement devices, and these measurement devices are usually very expensive. Uh, the cheapest one can start about $12,000 onwards, and you don't need only one of those. You need multiple layers of those, and each device of those would pile up on the other one. So to have a facility that is able to test microphones polar pattern consistency, sensitivity, to do the proper to be more consistent with another. Like if I build a microphone today, how consistent that microphone can be with the other microphone tomorrow. The facility will not be less than $150,000 to $200,000. And of course, companies that is trying to build a microphone just to do a quick buck, they cannot afford doing that, because if they start doing this, it doesn't make sense anymore. They want to sell the microphone for $10 just to make a quick buck. So if the investment is $200,000, how many microphones they need to sell before they just recover their investment? So to make a polar pattern very consistent, this is not easy. The other thing is if you try to buy any of those microphones just for the curiosity, and you try to check the consistency of the polar pattern and how much they reject the sound, you find they're not very useful. And you find that a lot of those microphones don't even follow what they have written on them. I've seen so many microphones trying to do a super cardioid, and that they're not even properly made as a cardioid. They tend to feedback easily. The other part here is that the pressure on the diaphragm as well is not consistent. So the way they build the diaphragms as well is not very accurate. So there are many, many, many points here that we can look into, and you can find that a properly built microphone should have a lot of checkpoints that makes it pass to be more consistent. We will have another session that will talk about the quality control. It's like a virtual factory tool that I will take you to. I'll show you some pictures of the factory and the quality control, and that would give you an idea on how sophisticated it can be to have a factory building microphones versus, just taking it as simple as coil, magnet, and a diaphragm. Of course, last time in the last webinar, we explained that, and we did some demos using an old speaker. Yes, it works. It's perfectly working. But by the way, if you get two speakers that are identical and you use them as microphones, you will fail miserably more than if you use these as speakers only. So the microphone, to be very consistent, because you're talking about a very sensitive part of the audio chain, smallest changes in the diaphragm can do a lot of changes in the audio chain. Using a diaphragm with a coil and a magnet as a speaker, you have more tolerance here towards little things versus in a microphone. So a simple example can be, as I said a few minutes ago, just by taking the grill off, you are changing this microphone from an SM58 to an SM57. So the foam here and the shape of that grill bowl, which is creating a bit of distance from getting close to the microphone, just creates that small difference between an SM57 and SM58 in the tonality. But if you take that off, it makes this a 99.9% an SM57. But you can see that the difference is not in the build of the microphone, it's in the very minor stuff related to the grill. there's another experiment that I usually do, which is talking about the pressured air, not pressured air, let's say the space behind the microphone here. So behind the microphone here, there's a chamber. I'll talk about it now, later on, but I'll do an experiment telling you on how even that affects the tonality of the microphone, which is quite bizarre for something that looks that simple. It's just like, isn't this only the handle to be able to hold it and not letting your ice cream bowl fall off? No, it's more beyond that. So we'll get to that part in a bit. And that is the interesting part. The Shure pneumatic shock mount. I remember last week I've talked about the shock mount very, very briefly, but this is always my favorite part in any of the webinars or in my trainings. When I first got exposed to this part of the microphone, I was literally blown by how sophisticated in terms of identifying that kind of technology to work for us. Though it looks very simple, but it makes a big difference. So does a shock mount hold up? That is a question that is related to this slide. So the shock mount is pretty much acts like a shock absorber for the microphone. So just like riding a car without shock absorbers on a rough road, you end up really tired just from the vibration on the road. Now, this part is as well one of the most complicated parts that counterfeit microphone manufacturers cannot attain to. Is the reason why is that, first of all, the calculations required to make the similar shock mount by somebody who has not did the calculations is not the same. The most important part here is that it is, if I try to put it this way, imagine if you're driving on a road and you're able to predict the size of the hole that you're gonna fall into and jump just before it happens, in which the hole that the car is gonna fall in, it will fall in and come out of it and you're still up in the air. So if I give you this kind of challenge or that kind of problem in a physics equation or in a physics exam, of course, all of us might have studied physics at a certain time in their life. And I know that physics teachers love these kind of questions. You're driving at that much kilometers per hour, and then in 10 meters, you are about to fall into a hole that is half a meter depth and it's half a meter long. What is the amount of force that you need to jump in order to pass above that hole without feeling any pain? Come on, let's do that, right? So imagine already we go like, wow, yeah, that is a problem. How can we solve something like this? And yes, you need to pretty much get a piece of paper, get you a cup of tea or a cup of coffee, put some music in the background, and you start noodling around with some equations. Because yes, it can get really tough. So let's put the same problem right now in context. I have a funny musician who'd like to always, do the trick with a microphone of throwing it around, or just tossing it left and right with a beat, or just doing the claps with a microphone, assuming that the microphone is that much grams, half a kilo, or 250 grams, or whatever the weight of this, and the weight of the hand from the musician is that much, and the force that he's applying on the microphone is that much. What would be the acceleration of the cartridge if the cartridge was loose? That's my bird. And then what would be the landing of that microphone cartridge, what the deacceleration is, and then how much do I slow down the microphone? And then you put this equation down, and then you realize that it is a serious equation. So let's go forward and see what musicians do. So Roger from I think he's from The Who. He does a lot of tricks with the microphone. Give me a second. Let me just put this bird back. Sorry about this interruption. So a musician likes to swing his microphone or throw it and then pull it back again, like a fishing technique. And then here we go, talking about the pumping pneumatic shock mount, which was the first in history in terms of resolution for microphones. So I did a quick test a while ago with the Super 55 or the 55SH, which historically got the same construction of the early microphones. So I'm gonna plug that in and let you hear how much of noise it can collect from the body of it. So you see that even the little. So the idea of tossing a microphone that time was not even there. The reason why is that, most of the time it's on the microphone stand, always there. People might move the microphone stand, but the recording was not still hi-fi yet. It started to get introduced, but the more the recording started to look at the lower frequencies and more higher frequencies into the recording, stuff like this started to go in consideration. But let me do the same kind of tossing on the SM58. This is the SM58. If I do the same thing with the 55, it'll be way louder. Even rubbing my hand is very minimum. So what happens here is that the shock mount built in the microphone is able to absorb a lot of that energy to let it go into the cartridge of the microphone. And that was quite revolutionary in these two models, the 565 and the 545, which were the early models of the SM57 and SM58. Someone asked me a question a while ago on why these microphones were like in the 60s, and let's say why they made it so big, why they were like very revolutionary. And the answer to this was two things. Number one, the shock mount was introduced for the first time in microphones. The second thing, microphones became possible to be held like this versus held like that. Now, a lot of people still like this, and I understand why, because it's vintage and it's lovely and it looks cool. But, moving from this into this, obviously that was way more effective. And a lot of people now recognize the shape of the microphone from these two microphones here. Those two shapes were actually engineered in Shure, and they never patented. So everybody else was able to do the same shape of these microphones. But if Shure have patented these shapes, trust me, until today, companies would have struggled to make a microphone that would be easily to handle. A good example to this is how Fender, for example, is dominating the shape of their headstock. They even dominated the shape of their guitar shapes. And just recently, some companies found a way to do the same shape with a little bit of tweaks that they will not go in a lawsuit against it with Fender. So that is actually quite lucky to a lot of the manufacturers. So the pumping pneumatic shock mount, as the name sounds like, that means the shock mount is relying on pumping air. So moving forward here, it's the way to mount the cartridge. So back to opening the cartridge. You can see that the cartridge is kind of suspended. I'm not sure how much I can show that on camera, but I'll try to get close here. If I get close, you can see that the cartridge is not totally mounted on the body. It's kind of suspended. And this is the beginning of how the shock mount is kind of connected. So it's the way that you need to bond the cartridge, but not totally get stuck to it. So you can hear that right away when I plug in my microphone here. So holding the body, you can hear a bit of the low end. It's absorbed a lot. But look what happens when I try to touch the cartridge here. Even the little. I'm doing the same on the body. So you can hear there's a big difference. So that means the cartridge is suspended, but not totally connected. Now, the cartridge is mounted on a chamber, okay? And the chamber here, which is C1, is also mounted inside the piston, which is P2. So the chamber is actually part of the piston. You can call it P1. And then it's mounted inside another piston, which is called P2. And then on the edge, there's a soft compliance mount. And between P1 and P2, there's a kind of resistance. What kind of resistance is that? This is like an air resistance. So how does this work out right now? So you remember when I opened the microphone, I told you there's a chamber at the back here, or there is a trapped area at the back, which means the air at the back of the microphone is also constant. So the amount of air at the back does not change. You cannot inflate or deflate that. So when there is a movement that happens on the microphone, the cartridge jumps in and out with a certain amount, forces the air from P2 to flow through the resistance into P1 and then to the back of the diaphragm, which means you're actually inflating the diaphragm just about equal to how much motion you're adding on the microphone, which works in reverse as well. Just like how the phasing happens by removing the sound, it's the same way. So if I try to move the diaphragm right now here, the cartridge, you would hear the sound actually. That is the sound of the diaphragm moving up and down into the magnetic field at a very low frequency. So if you have your microphone connected to your mixer and you have a woofer in front of you, you can actually see the woofer moving in and out without hearing a lot of sound, but you can see it just because of pulling the diaphragm in and out. Okay? Now, that explains also that the cartridge needs to be of a certain mass. So just muting this mic. I have here a SM57. This is an SM57. You can see here there's a big amount of metal mass. That adds more weight to the cartridge. So what happens here is that this amount of mass in the cartridge is actually just right to create the movement of the cartridge in and out of the handle. If the cartridge was very light, the shock mount will be less effective. So you can see that the way to achieve a shock mount is not straightforward, easy. Just put some felt on the side and let it happen. And you'll see a lot of the karaoke microphones that comes usually shipped with a lot of the stereos. They usually use just any microphone. Some of them, they use a felt on the side, like a rubber felt. And that's how you can actually even pull the cartridge out. And when you pull it out, you can see the wires. But this is not even efficient to make any kind of a shock mount, because the shock mount gets way more complicated than just isolating the metal from the cartridge. You remember the problem, solving physics problem? This is a actual calculations that was done in history just to find out what are required for the shock mount to happen. This is an interesting graph here. So one information I learned that was quite impressive is that the SM58 or the 57 has one of the quietest shock mounts in the industry. And when I say in the industry, like among a lot of the manufacturers. I'm not trying to compare here, but in this graph here, there's another microphones that we picked up. We didn't want to name any of them except the Shure SM58 to make it just interesting. And so we not put down anybody else. So at 90 hertz, and 90 hertz, this is where the most of the annoying vibration happens on stage. So when I have a microphone stand on stage, usually under the stage, we have the subwoofers, or at least in front of the stage, which also creates the same kind of vibration on stage sometimes. But also on stage, you have musicians dancing or jumping, or you have a drummer in the drum kit who's actually kicking the kick all the time and it's creating a lot of vibration on stage, plus many, many other things. And most of the annoying vibrations happens at around that spectrum between, 80 to 90, close to 100 hertz as well. But that is where the microphone is sitting on your stand. So your stand is on the stage, it's holding all the mics, and this is where you don't want the microphone to pick up the vibration from. You want it to isolate it. Now, of course, using a microphone stand that has a rubber felt in the bottom is good, but still, it's still going to vibrate. If it didn't vibrate from the stage, it's going to vibrate from the musicians, who's going to be either dancing with the microphone or, just jumping next to the microphone for any reason. So looking at the graph, you can see that the green line, which is the bottom one, that is where the SM58 is representing. And the maximum rejection is at 90 hertz. But if I want to ignore that and kind of look at anything else, at the maximum sensitivity for the vibration, which is happening at around 150 roughly here. So 150 hertz, it's still at minus 62 decibels. You know what minus 62 decibels is? Simply it's, if I have a fader, I was trying to pull a fader here. So your fader on your mixer, when it's on the top, just close to the top, it's usually at 0. Usually the minus or the bottom where you put it all the way down, it's usually minus infinity, but the first one coming above it is minus 70. So your mixer fader, when you push it all the way down, it's minus infinity. That means it's dead, it's quiet. The first line that you push your fader up to it, it's minus 70. Okay? So when I say the microphone is maximum sensitive to vibration just at minus 65, so as if the vibration was on maximum and you push it down to minus 65, just that first 2 dots on the bottom. But when it comes to 90 hertz, it goes down to minus 78, which is close to minus infinity at this vibration, which is very, very impressive. But the most important part, let's look at 400 hertz onwards as well. It does not exist. So what we see in the graph here on the slide is actually what the maximum vibration on the microphone is. But aside from that graph that we see, the microphone is not even there. Now, all the other colors here that we see, the yellow one, the red one, the sky blue, and the blue, including the orange, these are properly built microphones from well-known manufacturers, but the shock mount that they have was not as effective as the SM58 was. So this gives you an idea that being the pioneers in the industry in designing something is not in vain. It actually holds a lot of water here. And until today, in most microphones, Shure has one of the quietest shock mounts in the market on all the microphones. The pneumatic shock mount that was built in the SM58 was actually quite improved also in the beta series. So I have a beta 57 here, which is very similar to the beta 58. So this is the beta 57. You can see that the shock mount is quite effective here. And I'll try to show you the same thing, that it is also suspended. So you can see that close to the camera better. So you can see it's like a piston. It's not really mounted in. And moving it in and out also causes the same kind of noise. You can feel the diaphragm moving because I'm forcing it in. But also the cartridge is in a sealed packaging inside, where there is an air pressure that works and contributes in changing the diaphragm movement. There's another experiment I wanted to do, which is a kind of a proof. Let's see. Does the air at the back even contribute in the sound of the microphone? Let's hear that. So what I'm going to do is I'm going to plug in the microphone and check 1, 2. Hey, hey. I'm going to open the microphone here and check the sound of it in the air. So without a chamber at the back. Check 1, 2. Check 1, 2. You can see that the low frequency has changed just by talking to the microphone in the open. Check 1, 2, and check the sensitivity to the vibration. It's becoming more sensitive to vibration just by putting it back again in. You can see how much it absorbed the sound. So you can see that the amount of air trapped behind the microphone contributes in both the sound and the vibration. Moving forward, that will be the subject for next week, which will be the factory tour and how the testing procedures are done, what machines are used, and what are the things that we pay attention to in terms of manufacturing microphones and even quality controlling them. And probably to a normal user or anybody else, when you buy a microphone, you assume the testing is, plugging it in, checking does it make a sound, and that's it. But one thing I can actually just kind of use it as a teaser maybe is that the sound of the SM58 that we have today is typically exactly the same sound of the SM58 that was first built into the market. It sounds exactly the same. There is no difference. And to achieve that, it's not an easy task. I can tell you a glimpse of this, which we will see down the line in next webinar, is that the amount of tolerance that we allow in microphones less than 1.5 decibels. And when I say 1.5 decibels, that is throughout the curve of the line, like of the microphone's frequency response. So if the microphone and the quality control does not follow the same trace within 1.5 decibels, this microphone will be rejected and it'll go to the shredding machine. So this is a good indication that whenever you meet any engineer and he asks for a certain microphone, let's say, let's plug in a 58 or XYZ instrument, or let's use this microphone for that, or let's put two 57s together on a guitar cab and achieve a certain sound. This means that, first of all, it's like having a meal that you even expect the flavor of that meal before you eat it, because you know it so well from that particular cook or from that particular restaurant. The same thing as in tonality of the microphones, because the tone of these microphones was consistent for decades, is that engineers recognize the sound of those. I've met with one of the engineers from a mixing board manufacturer, and they were telling me a story about the way they developed the preamps of those mixing boards. So he was telling me that, we picked up X microphone and Y microphone and this microphone to find which of the preamps that they built for those mixing boards is going to give them the best results. And then they called one of the very, very, very known engineers back in UK, and they asked him to kind of give them feedback. I mean, just like everybody else. So he asked him, "Can you give me an SM58?" And the guys there were quite surprised. It's like, from all the microphones and all, like, there's more expensive microphones from Shure and other than Shure, but like you've chosen the most known microphone and a very standard microphone. It's like, I mean, is it super amazing? Does it have like outstanding characteristics? I would say no. It's just a standard microphone, but I mean, it's one of the very good sounding microphones. Does it make your sound better than usual? No. Does it make it worse? Of course not. But it's perfect. It works. And he said, I know the sound of this microphone by heart, that if I speak through any preamp, I would tell if the preamp is changing, adding, or subtracting anything. So he plugged in a microphone, 58. He used it a few times. He plugged it into that second preamp, check, hello, hello, hey, hey. Said, this preamp over that one. It was so simple, but it goes back to the basics, is that I know the sound of this microphone by heart. I know what to expect from a preamp when I use this microphone. And this only happens with consistency. And trust me, there are many companies out there that does microphones. And one of the toughest things is keeping things consistent, sound-wise, same way as people expect it to be. And one of the main reasons is keeping all of this laws of physics under their hood, and like making sure that this is happening. So next Monday, the session will be a blend of testing the microphones in the factory, so like a quick factory tour. And then the second part of that, it'll be gain structure. And this is one of my favorite topics, the gain structure, on what we really like or what is the right amount of gain on your preamps to make the microphones work without feedback, number one, and by getting the most adequate amount of signal into it. So this ends up the webinar for today, and it takes us into the this gives us a time for putting the questions and answers for everybody, including anything that they want me to highlight. So the platform is ready for you. You can feel free to put your questions and answers in the box, and we will answer them one by one. By the way, we will start doing webinars in Arabic. So the same episodes that passed before, I will repeat them in Arabic. So anybody who likes to attend those will be more than welcome. We will select a day for this. I was about to do a poll. I don't know if our moderator is happy to do that, to throw in a poll, and then maybe you can vote for which day you'd like the Arabic webinars to be, either a Monday or Thursday. So that also can be done if you want to suggest that directly without the poll, or just use the poll to use that to select the dates. But any questions for now, you're more than welcome to ask, either about the shock mount, or you can ask about uh, the polar pattern build of the microphones in terms of how was it built. Okay, so it seems there are no questions so far. So we have the poll right now. Please feel free to start on the poll and nominate a day that you think is more adequate for Arabic versus English. So let's say English can be on a Monday, and Thursday it can be the Arabic or so. So there's a question here. Okay, so the question here is saying that this this guest was confused in how phasing can create a different polar pattern. Okay, let's try to simplify it if we could. The thing is, I need two identical microphones, but unfortunately I couldn't. Okay, let's put it this way. And I have a microphone on the table here. Okay, if it's standing still on the bottom, that means there is no force on it. Okay, now what does phase mean, or how does the phase represent direction? When I say phase in physics or in a waveform, because usually the direction of the waveform is related to the phase. Okay, now when I say out of phase, that means it's 180 degrees in reverse. So it's simply, what is 180 degrees? If something is moving this way and I go and say the other object is moving 180 degrees, that means it's moving this way, because there's 180 degrees shift in phase. Okay, so that means if I have a force moving that way and I create another force with the same magnitude moving 180 degrees or out of phase by 180 degrees, then it's going to move in the opposite direction. And two equal forces moving in an opposite direction equals to 0, because that force minus that force equals to nothing. Now, creating that with two different microphones is impossible. It's like having two different magnitudes against each other. So there'll be a cancellation, but not total cancellation. But I'm 100% sure that a lot of you experience noise canceling earphones or headphones. And the moment you switch on the noise canceling, what happens? You feel something like it's a vacuum. It's like suddenly everything is kind of sucked out and becomes quiet. Okay? So the way the noise cancellation works is by creating the same sound at your ear reversed by 180 degrees. But that is why also you are still able to hear a little bit of sound from the outside, because the cancellation is not 100% efficient. There's still a little bit of leaks, but still it's very effective in major noisy sounds like rumble, AC rumble, a fan in the room, or probably a sprinkler that is working outside, or maybe a pumping motor that is on the roof. Consistent sounds are easily canceled usually by the noise canceling by creating an out of phase signal at your ear with the sound outside. Now, the same method is used in the microphones in sounds coming from a certain direction. So when a sound is coming from the back, there is a way to receive that sound and change the phase of it in which it causes some canceling with the front sound. That means it's less sensitive. So I hope that answers the question as much as possible. And understand a lot of the subjects that we talk about when it's coming in depth might be a bit complicated in terms of explaining it in physics, but I'm open to ask me another question anytime later on. If you go and research about this a little bit and come back again with more questions, I'll be more than happy to elaborate on this. So we have another question here. How to avoid phase issues when put two mics? That is a very important question. Phase issues will happen always when you have multiple microphones on stage. And it's something you can avoid by picking up the right polar pattern. So when I've spoken about the polar patterns a couple of weeks ago, I talked about the difference between the supercardioid and cardioid on stage, which contributes in less phasing effect. The reason is a cardioid polar pattern has a pickup from a 90 degrees. So this is a 0, this is 90, and this is 180. So from 90 degrees, it's still able to pick up the sound. An example to this microphone that I'm using here is a cardioid. So if I push the microphone to the front here, this is almost a 90 degrees right now. You're still able to hear me. You hear more room, of course, because I'm not directly to the microphone. But when I'm speaking directly to the microphone, you still get the sound now clearer. Now, with the supercardioid microphones, the amount of rejection starts from the 90 degrees onwards, which means the amount of leak that would come from the side of the microphone in terms of how much rejection, it's way more than the cardioid. So then if I need to use multiple microphones on stage, it's very recommended to use supercardioid for that reason. So for example, if I'm a percussionist and I'm playing, bongos and congos, and usually you have one microphone for each one of them. It's good to have then the Beta 57 instead of the SM57 in that case, especially if the percussionist is heavy-handed. That means if he plays that one, you want minimum leaks going to the second microphone, or you want the angle of the microphone to be narrower. And usually supercardioids are more narrower. So this eliminates a lot of the phasing on microphones on stage. But with that mentioned as well, sometimes we intentionally use the phase or the phase inversion on stage to be able to eliminate certain sounds or certain behaviors of microphones, which is called gain sharing. We will talk more about that on Sunday. Now, gain sharing, that means when you have multiple microphones in the same space opened up, the total gain from those microphones increase. So what happens? Normally, if you're engineering on stage and you're doing the monitors and you have monitors on stage, the normal thing to happen is feedback. So let's say I have a choir. Each person in the choir is having a single microphone and they are sharing a couple of monitors or a single monitor. What happens here? If you have 5 microphones opened, the gain is more. That means the whole system has more gain or more sensitivity, which means feedback will happen. So that means I need to reduce the gain or play a little game with it. And one of the ways to do it is inverting the phase of 2 of the microphones. So if I have 5 microphones, I invert the phase of the second and the third microphone. I put them out of phase by 180 degrees. So that means the gain sharing will be effective only for 3 microphones out of 5. So that means I keep the gain structure stable. But we will talk more about this on Monday's session. Hope that answers the question. Do we have more questions? So far, a lot of the audience want Monday to be the Arabic session. So far. Okay. So with this, it comes to conclude our webinar for today. Thank you everybody for attending our webinars, and hope to see you soon on the next one on Monday. Hopefully, as per the polls, it's going to be an Arabic session then for the first webinar that we had. So for our Arabic audience, tune to us on Monday for the first episode of our webinars in Arabic. And then the second one, which is going to be the Thursday webinar, that will be the continuation of today's. Thank you everybody for being here today, and have a safe evening, and see you soon. Goodbye.